we have the second order differential equation that represents the damped harmonic oscillator. My double prime plus by prime plus ky equals 0. What do mb and k represent? M, mass. What's b represent? Yep, the damping coefficient. And what's k? The spring constant, yeah. No. Okay, so we're going to talk about the harmonic oscillator. There was some work in your activities for 2.1 on the undamped harmonic oscillator. So I'm just going to remind you what that is. So the undamped harmonic oscillator, or frictionless harmonic oscillator, is a mass on a spring that oscillates, and there's no friction, so it's going to oscillate forever, right? So its solution would be something sinusoidal, if you wanted to model that motion. And then we derived this y double prime equals negative k over my to be the undamped harmonic oscillator. And I'll remind you how that works. Okay, so we started with the equation mass times acceleration equals force. Okay. This was in your activities. If you haven't gotten to it yet, you'll see it when you get there. So acceleration, if y is representing position of the spring, how could we represent acceleration? Instead of an a, we could use y double prime, right? Acceleration is the second derivative of position. So this says m times y double prime. And then force, there was Hooke's law about springs, that that equals negative k times y. So the force of the spring is proportional to the position of the spring. Okay, so this, when you solve for y double prime, is the undamped harmonic oscillator. And if you solve it for y, you'd see that the solution is sinusoidal, which makes sense. If there's no friction, that mass is just going to continue to move forever. All right, but if I'm going to add a damping force, most easily thought of as friction, right? There are other damping forces, but friction is the most easy one to visualize. We need to add a term for the damping force of friction. So a damping force slows the motion, it dissipates energy from the system, and the assumption we're going to use is that the damping force is proportional to the velocity, right? So the faster that mass is moving, the more friction is generated, so the larger the damping force. Moving slowly, friction has less of an effect. So on my force term here, I'm going to subtract, because damping is going to dissipate energy from the system. So I'm going to subtract something proportional to the velocity. And instead of writing v, I'm going to write y prime, because that's the derivative of position is velocity. And then just divide everything by m, right? So I have y double prime is equal to negative k over m y minus b over m y prime. And that is the damped harmonic oscillator. And when b is 0, you have no damping. So typically we simplify this equation. Instead of writing k over m and b over m, we just use, we let p represent b over m and q represent k over m, right? So you just have y double prime plus py prime plus qy equals 0. Solve that thing for, put 0 on one side and rename the coefficients so they're less confusing looking. All right, so I want to convert this to a first order system. So this is a second order differential equation because there's a second derivative in it. To convert it to a first order system, we say, okay, well, we can let y prime represent velocity, and then velocity prime, v prime, the derivative of velocity is acceleration, or y double prime, right? So to get my v prime equation, just solve for y double prime. And I have py prime, sorry, negative py prime minus qy. But the idea is I don't want to have derivatives in my equations, right? A system of linear equations, like you have a derivative on the left and then the right side is just the variables. So what could I replace y prime with? V. Yeah. So that's how you can convert a second order differential equation to a system of first order differential equations. Exactly. Yeah. You just assign a new variable that gets rid of the second derivative. And when you're dealing with position, velocity, acceleration, your new variable would be velocity. All right, so I want to be able to study some solutions of this differential equation, this ordinary differential equation, the second order damped harmonic oscillator. So we're going to try to guess some solutions. We're going to start by choosing some arbitrary values for P and Q so that we have something to play around with. So this is an example of a damped harmonic oscillator. So a solution y of t, something that solves this thing, it would have to be a function whose second derivative can be expressed in terms of y and y prime and constants. I have to be able to add the second derivative, the first derivative, and the function itself and get 0. Right? So those three things would have to be like terms. So what kind of function? The exponential. Yeah. So we're going to guess that my function y of t is some exponential e to the s t. And then I'm just going to plug into here to figure out what s has to be to make this true. So I'm going to do that on the next page. Y double prime plus 3y prime. Right. Okay. So if y of t is e to the st, what would y prime be? S e to the st. And y double prime? S squared e to the st. So now I'm going to take those three things, plug them into my differential equation, figure out what s to choose to force that thing to be true. So my y double prime is s squared e to the st plus 3 times y prime, which is s e to the st, plus 2 times y, which is 2 e to the st equals 0. All right, every term in here has an e to the st in it. I'm going to factor it out. And I'm left with s squared plus 3s plus 2. All right, so now I have two things being multiplied together. The answer is 0. What has to be true? One or the other, right? To get a product of 0, one factor or the other or both has to be 0. E to the st has to be 0, or s squared plus 3s plus 2 equals 0. All right, e to the st. Is there any s value that would make that 0? No. Exponentials, like picture a graph of e to the t. It has an asymptoted 0. It has no zeros, right? So this is never. Right, and s squared plus 3s plus 2, that we can factor and get zeros. So I have s plus 2 times s plus 1. Set each factor to 0, and you get s is -1 or -2. So I've actually found two particular solutions to this second order differential equation. I haven't found the general solution yet, but I found two particular ones. So I'm going to write that here. Two particular solutions. Y1, we'll call it, is e to the negative t. And my second solution is e to the negative 2t. Just e to the st, where I used those two as my s's. So it's kind of a nice thing about the damped harmonic oscillator is that you can always find some particular solutions by using this guessing technique. It's just very similar to the lucky guess technique we used for linear equations before. Yeah, because before we knew we were looking for like alpha e to the, we knew what the exponent looked like. Yeah, so now we don't. We know less. Nope. Yeah, just a new way of guessing. So here's my direction field for this system. Here's a really annoying thing. It's very annoying to me anyway. When you take the damped harmonic oscillator and change it to a system, so that we did that earlier. We got y prime equals v, and v prime was negative 3v minus 2y, right? When you create a phase portrait, a direction field to make a phase portrait, your y is your horizontal axis and your v is your vertical. Super annoying because you always think of y as being vertical. But y is your first equation that shows up here, so it's going to be your horizontal. Because I'm thinking of y as position, yeah. Yep. All right, so I'm going to sketch some solution curves that correspond to these two particular solutions we just found. So let's think about the one for e to the negative t. There's some curve in this picture that corresponds to that y1, e to the negative t. Okay. So this picture has y position and v velocity. I only have an equation for y right now. How could I come up with an equation for velocity? Y prime, yeah. So v1, right, that goes with y1 would be negative e to the negative t. So I'm closer, right? So now I have a formula for y and v. I need y and v because they both live in this picture. I need to know stuff about y and v. How could I figure out my initial condition? The way I normally use this direction field is I plot an initial condition and then I follow the arrows. Initial condition means where that point is at time 0, right? Okay, so how could I need to know the position and the velocity at time 0. Yeah, we're just gonna plug 0 in here, right? So y1 of 0 is 1, v1 of 0 is negative 1. So I plot the point 1, negative 1. There's my initial condition right here. And I'm just going to follow my arrows, and it looks like it's sort of curving into the origin. And then I'm going to also do this for the other particular solution we found, y2, which was e to the negative 2t. So y2 is e to the negative 2t, which means that v2 is negative 2 e to the negative 2t. Plug 0 into each of those. So y2 of 0 is 1, and v2 of 0 is negative 2. So I have a new initial condition, 1, negative 2, position velocity. 1, negative 2. Here's my initial condition. Use another color. and I follow the arrows in towards the origin. All right, so that's it for the demo. You can use the rest of the class to work on the class activities for class 23.